begin recording now. Okay, so for the topic itself, in terms of the magnetic stripes, people began to do it about 100 years ago. So that was a time started from the navies, for example, in the US or probably in the UK or some European countries too. So it started from military that people did the seafloor survey for different purposes, mainly for the military use back then. And then in the I didn't remember the exact time, in 1930s, 40s, and people began to find some this symmetric patterns, magnetic stripes along the axis of the different reefs. So I bet the very first people who noticed that should be people in the navies, but they are not academics, so they didn't publish papers. And later on, when the academic community began to realize that, and people proposed like the seafloor spreading hypothesis, and later on that was used as a key evidence for plate tectonics too. So that's started maybe about 100 years ago, and then until 1940s, 50s, it became relatively mature for people to know what it is. And then for this magnetic stripes, a key part and key knowledge for it is the Curie temperature. Is that once the temperature fall below, for example, 580 degrees C for magnetite, once the temperature drops below that, then it records the magnetic field of the Earth at that particular time. So it could use it for different purposes, and for this work's purpose, then they trying to use that 580 degrees C is important isotherm file, so that they could basically map those samples in 3 directions. Arca, I cannot see your screen. Okay, please don't share full screen of your screen.
No.
Okay?
I have not shared full screen. It's in the PPT mode only. Like in the normal PowerPoint window is only just open.
Okay. Okay. So for the cross-column itself, I think there's although I haven't done specific research on that, but I think there are a couple of things that are still weird to people. First, for this system, even the mass balance is not perfect. For one example is that when people calculate the mass balance for ferric iron 3+ through the mantle melting, and then you see that how much mantle melting you get, the mantle melts and form the oceanic crust. And people calculate mass balance and find that doesn't match with the crustal thickness of today. For example, we have, let's say, 8 kilometers, 6 kilometers Earth crust, and when you do the mass balance by ferric iron, it's not. So, and also for various element, when people choose to explain through the equilibrium reactions, actually doesn't work very well from time to time, because for this melt generation process fundamental actually is a multi-phase flow problem that doesn't look like perfectly explained by the equilibrium. So a lot of people also work in that direction. And for this work, they're trying to do something that basically combine the seafloor survey as well, basically by some deep dive vehicle. I think it's pretty interesting, as well as the samples that they collect. Basically, you could measure in the laboratory, and then you combine those two together. You could map them in 3 dimensional. Basically, they use one example in this fastest spread field. Basically, you could apply to the world, whole world if possible. And for the work, the key person actually doing this is Jeff Gee, the second author. Because he is a expert in combining both petrology as well as geomagnetics. So Sarah Meher is the PhD student working with Jeff Gee before. She just graduated a couple of months ago, and so she just implemented the idea. So with that, Arca, please go ahead to let us walking through the paper. But again, I mentioned to everyone, don't list the words. Future presentation, list the figures, explain the figures, or list the words in the construction of flow charts so that people could see what's the logic. Okay, go ahead, Arca.
Thank you, Dr. Zhang. I will take care of that part from the next slide. So a bit about the author. She did graduate from University of Hawaii, Mauna. Did a master's from there. At present, she is working on using magnetic techniques to find out how the Earth's crust, the cooling of the Earth's crust. Like Dr. Zhang said, she completed her PhD from the Scripps Institute of Oceanography just a few months back. So coming to the key points in the paper, uh, so the Earth's magnetic field, like well, the crustal cooling actually controls how the Earth's magnetic field is being recorded. So the polarity in interval boundaries, they are actually the proxies for the isotherms, and thus we can have a fair idea of the crustal accretion, the method of crustal accretion, if we understand the Earth's magnetic field, rather the magnetic strips we are talking about here. So this is what they have targeted into understanding using a specific location which is very well suited for the study. So uh, they particularly studied a Dike-Gabbro transition zone and found out why the temperature was constrained at 500 degrees Celsius over there for a certain time period in the geological time scale. So the results actually suggest that there was a robust fast spread oceanic crust, and they give the constraints to how to differentiate between a slow spreading crust and a fast spreading crust using the temperature constraint. So the interpretations from the thermal structure of a oceanic crust actually can give us a number of ideas. For example, the crystallization and the melting phenomenons happening uh, give us can be constrained to understanding that. So what do they mean by a third dimension study is that apart from studying the solid samples from the Earth, they also did a study using an auxiliary underwater vehicle, automated underwater vehicle, AUV, and they oriented the samples at the ocean floors and took scraps from that. So the seafloor magnetization actually provided a valuable information about the thermal structure of the gabbroic crust and uh, the process of the crustal accretion. So usually when boundaries, we get a polarity boundaries, reversal boundaries, the ridgeward dip is expected if the accumulation is from the lava. However, if the from this polarity boundaries, we can infer the then isotherms, and we can potentially differentiate between different kinds of cooling patterns. And for example, the pervasive deep hydrothermal and slower and more conductive cooling patterns requires gently dipping isotherms. So these are the basic fundamentals based on which the paper has been written. So they actually worked in pitot tectonic window. So over here, the fundamental idea is that uh, depending on the blocking temperature and the crystallization history or the cooling history, they could say that the number of magnetizations that were captured. So there were two coherent strips. They have named them, and the time is given. And so this were parallel to the abyssal hill of the fabric trend, and one third of the samples actually exhibited a broader distribution of blocking temperatures, referring that uh, their cooling was slower compared to others. So here is a idea of the area that they studied on. So over here with the red areas, those are marked. They are of the normal polarity, and the blue ones are of reverse polarity. So they drew the contour. The bathymetric contours are explained in the gray lines, and uh, the different zones or the magnetic strips are marked. Like you can see, the marked as crons, C2A and dot 2R, and so on and so forth. So So, like I said, that the magnetization was derived from a near bottom magnetic survey using a vehicle, and so depending on different meters below the sea level, the polarities were recorded, and they were most interested about the stripes that actually coincided with the magmatic processes like the dike gabbro transition zones, the or the portions where lavas and dikes were formed, because depending on the different types of magmatic activities or magmatic plumbing systems, what happens is that the record of magnetization changes. So according to that, they studied those paths. So here is actually the 3D or the third dimension magnetic strips that are being shown. So over here, you can see that in figure A, near bottom magnetization solution of two zones A and B are shown over here. So basically the cron 2 an dot 2n and 2r are, they fall under the area A, and dot 3n they fall under the area B. So the dashed lines actually locate the polarity boundaries where the reversals have happened. And in figure B, you can see the three-dimensional structure of area A and area B, and the related magnetic polarities and that were observed. So the theory is that magnetic remnants of samples that are oriented, obviously samples need to be oriented before doing any kind of magnetic paleomagnetic studies. So they give evidence for a subhorizontal polarity boundary in the upper gabbroic section. So the idea is that while the lavas they cool rapidly, lavas and dike that cool rapidly, they record the polarity interval, while the slowly cooled gabbroic rocks they record multiple polarity intervals. So the highest temperature of the components that are acquired during the later cooling, most gabbroic samples have a remanence of 500 degrees Celsius. But this was not in accordance to the isotherms, or they actually, the portion that they were studying was the first spreading range. So the slow cooling couldn't be explained. So this is a 3D structure. If I don't zoom it in, I don't think this part is understandable. So I'll just. Is it readable now, or should I just increase it a bit more?
Is it readable? But I prefer you to show the figures larger.
Yeah, because I actually planned for doing a full-fledged PPT presentation, but for some reason it's not working.
No, I think even is a full screen, you should still put the figures as large as possible so that people could see it.
Okay. Okay, so I'll just 1 second. I'll just move this. Okay, so okay, so this is on the y-axis we have the depth, and on the x-axis we have the boundary from. So this is basically from the ridge. It's the away from the ridge we are moving. So these are the initial lavas that are formed, beginning there. Then so as we move away from the ridge, so the spreading center. So this is the 3D diagram given. So so what happens is that the near bottom magnetization solution, the oriented samples. So over here we can see that the oriented samples are shown in circles, and the previous studies from the samples that they have taken are shown in diamonds over here. And using that, they actually they try to draw a 3D model of what is happening over there. So this is just a representative picture of that. And what happens is, the interesting part is over here, where they're saying that a fault has happened or an onset of faults happened. And this is actually one of the major conclusions of the paper, that due to this onset of faults, the cracks have developed, which actually allow for the hydrothermal fluids to move in. And that actually constrains the temperature in this part. So this is, in the maps, we have seen the plan view of whatever is happening. Over here, this is a 3D picture showing the same. So as we can see that there are over here, if we see the structures of the, if we see the distribution of the dotted points, so we see that there is a very prominent subhorizontal band over here, which shows basically there are normal polarity magnetization, there are reverse polarity magnetization. However, this subhorizontal band is very prominent over here. So on doing the reactions in the lab, and they got a mean temperature of something around 530, and they came up with a range of 500 to 560 degrees Celsius was the breakpoint where the magnetization was captured. So actually what happens is that the band of samples that we see is extended. They are not limited to one particular kind of, so the rock compositions also changes from gabbro to trocolite. And therefore, the cooling depends on the emplacement of the magmatic temperatures. As the composite changes, since the temperature also changes, so accordingly, multiple polarities are also captured over here. So I'll just skip through this slide because it says the same thing that I have said till now. So I'll just go through the major conclusions of the paper. So it shows that a shallow gabbroic crust remains sufficiently hot in order to support localized melt, consistent with the seismic studies. And it also agrees with the convex upward geotherm near a ridge as it was postulated in other studies. And the persistence of a 500 °C near the digabbro transition is limited due to the faults, which allows the penetration of fluids and hydrothermal venting process happens. And this model also predicts a brittle failure at 700 to 800 °C at a pressure of 100 to 300 megapascals. So this model was able to constrain the location of isotherms of relatively fast spreading axes. And here is a structure of what a very detailed view of area A, which they did through the bottom magnetization solution and of rock samples. So the rock samples was collected, like Dr. Zain said, and the bottom magnetization was solution was done through the automated vehicle. In the next slide, this is the same detailed area of area B, like detailed picture of area B, where we can see the different stripes of magnetization. So the conclusions differ from the previous works in a way that the model shows that due to the presence of the subhorizontal polarity, which extends out from the axis, the cooling rates, they were able to correlate the cooling rates with the magmatic activities happening over there, as it was suggested by geospeedometry studies. And there was another theory that while this expansion or this spreading happens, latent heat actually spreads over a broad zone. So this spreading was also over a broad zone, and actually this delays the conductive cooling, but that is for a lower crust. And if what happened is that previously it was not incorporated into studying fast spreading crusts, and that's why the correlations were not made correctly. So over here, this constraint was overdue, and they could do that. This is just a snap that they've taken from the uh, vehicle, and that how it actually orients and scraps up the samples from the sea floor below. So that is all about my talk today. So thank you.
Okay, Arka, thank you for sharing us the paper. Okay, any questions from the participants? Okay, actually, okay, let me share my screen. Okay, could you see my screen? I think
Yes,
you
your
can.
screen is visible.
So here, actually, when I'm reading this one, it shows that That circles and previous study diamonds. Actually, where are diamonds? Okay. So this are the 500 degrees C, right? These are not. These are the previous ones not defined. And then they draw the dashed line in 500 degrees C if it's extended further. Okay, that makes sense. That makes sense. Because otherwise it would be something like this, and then it cools down. So that this should be like, say, 800 degrees here, and drops to 600 degrees. Okay. Okay. And why the diamond or the diamonds around, Arga, or the diamonds here?
So I don't. I couldn't get your question.
So they say that this diamonds are 500 degrees isotherm that you would
Yeah.
define
So
before, which are these points, right? So and these circles are what they define this study, I suppose.
yes. So actually, what happened is that in the previous studies, they didn't take the concern. Like in the last point of my PPT, I said one thing that what they did was they considered that the release of latent heat. They didn't consider that the release of latent heat actually delays the onset of conductive cooling. So that was incorporated in like those were not incorporated in fast spreading crust models. So in this model, they used it, and also they did mention in their methodology something about that the methodology was a bit grasping with that because they didn't mention about whatever they did in like whatever instruments they used, but they didn't explain the what kind of modeling they used because the code is also not available. So it's a bit of a black box to me also that actually what are the parameters they said. They said that they did do some parametric studies, but what were the exact parameters they took into the studies, that is even a doubt for me.
Okay, so if they didn't consider latent heat for these examples, now people
Like they did
before
consider latent heat. The previous studies didn't consider the slow cooling part.
So yeah, so for the previous study they didn't consider. So could they recalculate based on the previous
Okay.
study?
Okay, I have no idea about this.
So yeah, or just leave their previous study as it is here, or they also could take advantage of that.
I think there's a question from someone.
Yeah, there's a question from
Okay,
Ben.
Ben asked a question. Okay. So yeah, so the magnetization direction and temperature actually, while anyone is doing a paleomagnetic study, like even a basic paleomagnetic study, so magnetic orientation and temperature study is not what they do. Like they know the blocking temperature. The blocking temperature of the magnetic particles are known. So they practically demagnetize the samples and then they heat it to the Curie blocking temperature to see in what orientation would they have magnetized. So that is known as the orientation of the magnetic samples. So I believe what they're trying to do is basically set a relationship between like the temperature that they're getting by orienting the magnetic samples and the magmatic activities of the, for example, while you are getting a lava, like a lava or some magma lenses, then we go for a fast cooling approach. But while we are getting a transition zone of gabbro to trocolite, we say that maybe the cooling was slow. Or for example, if a sample catches a lot of magnetic polarities, so we say that the sample cools slowly. Or whereas a fast cooling sample actually actually stores only one kind of magnetic direction. So that is what they're trying to do, maybe comparing with the lithology and the magmatic activities and setting the temperature of using a magnetic study. They are actually trying to correlate with the magmatic evidences that is my idea after reading this paper.
But I think what the Ben statement is not fundamentally wrong, because it is still true that you see these magnetic directions of the samples, and then you are trying to correlate them with the temperature,
Yes,
basically.
because
And then go ahead, Arga.
no, you were saying something. Please continue.
No, I mean what Ben mentioned about was not.
Actually, from the very basic understanding that I have, actually, like the people, I have seen one of them doing, one of my seniors doing paleomagnetic studies. So I saw them that they collect the samples like from the field. They come back, they actually demagnetize the sample. They know the temperature at which they have formed, like from previous studies or something. Then they reheat the sample to the Curie blocking temperature of if they have magnetite or other whatever magnetic samples, and then they measure the orientation. And they pick up samples from the field in a oriented way. So in that way, they can actually get the present sample, like the with the present attitude measurements. They relate the magnetic orientation of the magnetic particles. So I believe that any kind of paleomagnetic study actually works with, like, they do need a temperature resetting in any kind of magnetic study. So this is my that understanding I was saying this. But from the paper, I didn't understand anything like that.
Okay, let's jump to the next one. So Chen now asks, so does this study does any contribution to the crust formation? And I don't think so,
No.
because I don't think that's the key part of the paper. Because if we see the slide that I'm sharing, so the crust formation I think is here. So is at this axis, mid-ocean ridges, whatever, and then they form the crust. And this paper, I think, is mainly about the cooling. So how does this high temperature magma that erupted and cools? And normally their story ends at 500 degrees C. So once you are below 500 degrees C, I don't think that this work could add anything more to that, because then you once you're below the Curie temperature, basically you observe what it is. And yeah, so I don't think this work does any contribution to crust formation in terms of the magma perspective. However, if you talk about how does this, if I change another word into Trina's question, does this work make any contribution to help us understand or shape our understanding of how the crust forms to what it looks like today? Then I think that they make some contribution. So, so yeah, because if they some parts of the dikes, I would say the gabrels, they are cooled much more slowly, and allows this fluids or hydrothermal, whatever, and then expand this 500 degree C. I think actually to me that looks like it's also going to affect the crust thickness to a certain extent. I haven't came a very clear thought about that, but I think I do think that this work that does have an effect, does contribute to how the crust looks to what it is today, but not specifically in the context of how the crust was formed at the mid-ocean ridge or directly from magma. That's just my understanding. Maybe each of you could show how it looks like that.
I think I'll answer Urmidhi's next question. It actually deals with from the age of 3.30 MA, millennia back, and the magnetization period is reserved for around 0.1 million years in between that. So that is the time period they have dealt with over here.
I think one thing that they didn't tell, but I think it's hidden or is well known in the geomagnetic community, is that for the polarity uh, of these magnetic stripes, that we do know the standardized form. So from the recent 160 million years, uh, pretty much you sample the samples, get the samples from around the world, then basically at any given particular time, people wouldn't know. I would quote say, people wouldn't know the uh, Earth geomagnetic field at that time. So that basically that's where people could go to compare, and then actually that's how people date the ages of a particular oceanic basalt sample or gabbro sample, for example, uh, using the magnetic methods rather than radiogenic isotopes methods. That's another method you can get age. So another way is that you could get it from the uh, direction of the geometric of these magnetic samples, which with the assumption that people know the geometric field uh, polarity back then at this particular time. So it's more like a barcode for each particular time of Earth history after combining the global samples. Okay, maybe Ben, please share your screen.
Well, I just found this is cool. This is how they use this robot to collect the samples, right?
Yeah, that's pretty cool. Not only the graph samples, but also they basically, I think they are going to make the drills. Do they? Because they also have to mark the direction of the samples before they can retrieve them. Otherwise, then you don't know, people don't know the magnetic polarity of the samples. Yeah, because people assume, not assume, people, yeah, people do have to assume that the samples are intact since the time that they have formed.
Yes.
Actually, yeah, now more countries having that. China also have this deep dive vehicles now. Actually, yeah, last week I was having lunch with some other colleagues from the Ocean Institute here in Hangzhou, where they did also get some of this period samples from the deep ocean seafloor vehicles. Yeah, from China. I think in 2021, that was quite a real new dive that people got some samples. Yeah, it's kind of bizarre that people could let the machines dive and works in these very high pressure conditions, because basically they are like 5,000 meters away from the surface of the ocean. And actually it's quite a high pressure. Well, it's not that crazily high, but you still get, let me see, let's say 0.2 GPa in terms of pressure. But that's still large. You have all the vehicles work under these high pressure conditions, and people able to control them. I think there is a pilot. I don't know whether they have pilot. Probably they do have a pilot and a scientist sitting in the vehicle and operate them. Okay, any more questions or comments or ideas to share?
I think that you just said that about the orientation of the samples that they're taking. So over here, they made that assumption, or like the educated guess by through that the strips, magnetic strips that they're taken were in parallel to the abyssal plane. So that is how they took the fact that those samples were intact and their orientation has not changed. So I think
Mhm.
that was their way of studying, like choosing the samples over here.
Okay. Actually, it's interesting. I think this is what I guess, or is a wider guess, is that these samples are very few. So yeah, when people get very rare treasure samples where you don't see them everywhere, and I don't know whether this is the very first ones that people retrieve them from the ocean intact. I mean, for those IODP drilling, the International Deep Drilling Program, people go to drill the samples, and so that's how the deep samples coming from. In one way, another way is that people go use the different nets, and then those nets just pull the samples in the ocean floor. And actually, they pull it really far. People have many kilometers. So pull the nets in the bottom ocean, and then the ship sail for several kilometers. So then you get samples up. And for this one, people use the vehicle to went there and sample them. Then you see exactly where they are. So I think the samples are a little bit rare. And in particular for samples, their orientation. So I think that probably is to me, that looks like the most attractive thing that they get is that is unparalleled. You have those intact samples. So by that, I think the basically to me is like they did a map, they just did a mapping of the isotherm uh, of the lower crust. So yeah, to me, I sort of like could feel the same feeling of like turned out that this doesn't look like too dramatic in terms of how we really understand the crust forms or how the heat is lost from the Earth interior to the surface. Yeah, I don't think that it contributes to that level. At least I didn't see it. Maybe on Wednesday, the speaker could tell us more why it is so important. But I could see why it could publish in Nature. I don't think that for those very rare samples, if ever people just got it, um, uh, it's worthwhile to report in Nature. Although maybe the science contribution is not as much as what we hope that it could be, but I think it's okay. Yeah, we'll see on Wednesday to see how the speaker defend that this work is so important. Okay, I think that's so much today, and thanks very much for everyone for your participation, and thanks Arca for leading the discussion, and see you on Wednesday evening for the speaker's talk. Okay, see you. Bye.